Like my host said, I'm Matthieu. I work for the Muse group. I'm part of the Audacity team. And yes, indeed, I'm going to tell you about the tempo estimation algorithm that we released recently in Audacity. I'm going to begin with a demo just to make sure that everyone knows what it is that we're talking about. So just imagine that I opened Audacity for the first time. It is in its default view mode, which is minutes and seconds. And the tempo is by default 120. I'm dragging in a drum loop. And here the algorithm that we're going to look into kicked in. So it analyzed the sound, recognized that it was a loop, and then deduced the tempo to be 116 BPM. So we issue this little window here. Audacity detected this file to be 116 BPM. Would you like to enable music view and set the project tempo to 116? Yeah, okay, we say yes. Now I bring the next loop, which is also a loop, and it's also detected as such, but doesn't have a matching tempo. So it does the stretching to basically match the project's tempo. So we have a 90% stretch here. And indeed, we can see that it matches an exact number of measures, and everything looks and sounds in sync. So nothing revolutionary at all, but we're nevertheless going to look into this. If I bring in something that is not music, then here nothing happens. You see, it was not stretched. And indeed, the audio clip does not match an exact number of bars. So that's what it is that we're going to look at. That was not me. That was about 6 months ago that we released it. It came with Audacity 3.5. And then I submitted a talk proposal to ADC. I was delighted to be accepted. But in the abstract, one of my selling points was that although the algorithm was living in the Audacity monster repo, it actually had very few dependencies and could easily be extracted to an independent library. So I thought I'd verify this and live up to my word. So I did the work myself. Now the algorithm is in this repo, github.com, Matthieu, that's me, loop tempo estimator. It's indeed a lightweight library. It was also the occasion for me to review my algorithm. So lots of it are derived from textbook findings that I did or from existing solutions. But there is also a novel part to it. Part of it is like I probably legitimated by some strong scientific arguments, but a lot of it was also a little bit instinctive. And I didn't want to feel embarrassed in front of you, so I thought, okay, I really have to make sure that I get rid of any unclarities in my repo. And that had a very good side effect, that the code was indeed simplified. I indeed found things that did not make much sense. And the performance was improved by almost a factor of 2. So that's a big positive side effect of me being accepted at ADC. You will see, we'll take a quick look at the repo. It also offers a VAMP plugin, so I put the library into a VAMP. And in case you get bored during my talk and you happen to have a VAMP host, like Sonic Visualizer running on your computer, you may want to give it a try, but with headphones, please. And there is even this presentation in the repo. That's probably less interesting to you. So we take a quick look. Thanks very much for the contributors already to this repo. We have CI, so we have a release build, and in this release build you also find the binaries for the VAMP plugin, for example, for macOS, Windows, and Linux. Thanks very much, especially to Dmitry, who in these last days has really supported me a lot in that respect. Okay. The next question is it going to be integrated back into Audacity, right? So if you use Audacity at the moment, it still is this originally living in the Audacity repo version that it's there. There's been improvements. It's now more efficient. Are we going to integrate it back? So it's not going to be part of Audacity 3, whose development was frozen, because now we are really putting all forces behind the next major release, which is going to be Audacity 4. And this is not just a mock-up, it's actually the application. So we already can do a few things with Audacity 4. And I'd be more than happy to maybe give you a sneak preview of what it is going to be like. And by the time we release Audacity 4, then I will have done my lobbying to get my own sort of cleaned up version of the tempo estimation algorithm into it. Okay. I begin by talking about evaluation, and it shouldn't be surprising, actually, right? Test-driven development is something very noble, and soon enough, when I started tweaking my algorithm, testing it, I realized that I needed a proper benchmarking framework that to guide my development. I mean, I would make my algorithm work for a certain loop that I'm dealing with, and it would break it for other loops, and that was just hell. So I invested the time first to make myself comfortable, right? Evaluation. How do we evaluate this? We basically use a receiver operating characteristic. I don't know what that means. If you do, please tell me after the talk. But I know how to use it, right? And it's excellent for measuring how discriminant a classifier is. So we have a discriminant classifier here, the one that says, yes, it's a loop, or no, it's not a loop. This is the first step. The step where we detect then the BPM is a second step. So for this first step, which is the most crucial one, we need an objective measure. Just the perfect classifier would basically be this green curve here. And if you measure the area under the curve, then you get 1. That's the classifier who basically always gets it right. And the useless classifier is this orange line that would be just as useless as tossing a coin and see, okay, is this a loop or not? I don't know. Oh, yeah. So. Of course, I was talking about this to one of the attendees of the conference yesterday, the day before yesterday, and he actually immediately said, but that depends on your data set, right? And he's right. It does depend on the data set. If I use another data set, maybe that only has loops that are very, very loopy, and non-loops that are very, very non-loopy, then it would be very easy for the algorithm, and it would here get a very good score, right? So we are going to talk a little bit more about the choice of the data set in the following slide. But in the meantime, it's part of the regression test of the repo, so anyone who contributes, who modifies the code, makes a pull request, this is going to be run, and to verify that the arc is still the same, or that it has improved, but we will talk about this. How does the benchmarking framework is built? We first have it's basically going to invoke some Python command to download the data set if it's not already on your computer. We, of course, have to make sure that the input between consecutive runs stays the same, right? Otherwise, it just simply invalidates the whole thing. So the input has to be the same as before. If it's not, we fail. If it is, then we go into this iteration. For each file, we run the algorithm. Algorithm says yes, no, loop or not. And we then check this against the ground truth of the labeled file. And then coming out of this iteration, we can draw our rock, measure the area under it. And if it's a match, so we have the reference to the current arc is hard-coded in this benchmarking test. And if the new measurement says now it's different, then it's going to fail. Just a quick note that if it fails, it's actually not necessarily a bad thing, right? I mean, if the arc gets closer to 1, then we are getting closer to having a perfect classifier. but I still make the test fail because it still then is worth having a human being then look at why the behavior has changed and if it's legitimate to check it into the code, right? Okay, the data set itself, I've mentioned this already. I took a few minutes to think what would be the perfect data set, and I think it would be great if over the course of 1 hour, all import actions of all Audacity users on the planet could then become part of this data set. That would be a perfect representation of our user base. And if I then improved the ROC for this data set, then I would also improve it for all our users. And it's completely democratic then, you know. But that's not possible anyway because you would need the labels, right? The ground truth. So it's not practical, it's not possible anyway. But just to give you, I don't know, to make us realize that this ROC is not the ground truth. I may have a very nice score, and actually maybe my data set is completely biased. So I'm not making a selling point out of this, but at least from this benchmarking framework, what we can do is compare another algorithm. Then they would get the same input under the same conditions, and then we could compare the measures. So this is one thing also that it could be useful for. The data set then that I had to use, I went to freesound.org because the license under which the files are published there is the Creative Commons, and it's redistributable, and Audacity is an open source project. So when you run the test, we actually redistribute. So it had to be something redistributable. And they have a nice client API where you can query your files with some filtering. And they also have the loop tagging. So that was a good starting point. I began by downloading 100 loops and 100 non-loops. But the tagging itself is automated, and it also is imperfect. So I had then to do some human verification of each of these. That took quite a while. And I ended up then with 70 non-loops and 70 loops. So scientifically, it's very questionable, but it's much better than each time that you change your algorithm, going through all 140 files by yourself, right? I think you'd agree with that. So better than nothing. All right, and now we are taking a look at the algorithm itself. Beginning with the requirements. So we need a confidence value. The confidence value is actually the output of the classifier. So yes, this is definitely a loop. This is definitely not a loop. And then there is the gray zone, because if it's not a perfect classifier. So in the gray zone, yeah, maybe it's a loop. Here we set the threshold actually quite high for this use case, because Audacity is historically used by, and still largely so, by podcasters or scientists looking at sound, how it looks, making some analysis, and they don't care about music usage of Audacity. So at the Muse group, we try to bring Audacity to being a real DAW. We are not there yet, but we will get there. But we are going to make a sort of a hybrid application out of it. Depending on what use you want to make of Audacity, it's going to look and feel different. But we have to preserve as well this historic use of Audacity. So annoying a podcaster with, hey, we've detected tempo, while it's actually wrong, would just cause annoyance. We have to be very careful with this. And we do actually get a few complaints every now and again. But there you go. Short file support. Why am I saying this? I, of course, looked to existing solutions as well before reinventing the wheel. And the majority of them needed some duration before they could start asserting a tempo with some confidence. So needed at 5, 6, 7 seconds, not less. But loops can be much shorter than this. So these solutions did not really make it. Loop support, yeah, of course, loop support. If you drag in and drop a loop, it should be detected. But what I mean by this is, in contrast, some music that is rhythmically steady, that definitely has a tempo, that definitely could be stretched. If it's not edited as a loop, do we have to support this use case or not? Knowing that actually, if we want to this support, it makes the algorithm more complex and introduces a higher chance of us issuing false positives again. So a little bit of thinking said, no, we don't have to support non-loops because they are the minority, basically. And false negatives are not so bad. False positives are bad, but false negatives not so bad. And what happens if the person drags in a piece of music that has tempo? It was not aligned with the tempo of my project. You can still drag one of the edge of the clip and adjust it yourself. So it's not the end of the world. No big deal. And 4/4 time signatures, of course, has to be supported, but by contrast, 3/4, 6/8, 12/8 time signatures. I tried actually, and it's the way it is in the Audacity repo, but that doesn't really bring much value. The vast majority of the time when it's a loop, it's 4/4, and it brought complexity in the code and also more risks of false positives. Excuse me. So we are very conservative. We only detect loops if it's 4/4, and all the rest, ideally, we say, no, it's not a loop. And now we are going to look into a little bit more at the DSP side of things. The first thing we need is a nice onset detection function. When we get the input, it's a waveform with all the detail that allows the perception of timbre and everything. But it's way too much information. We reduce this to only what we are interested in to infer some rhythm. There are indeed many aspects that help you evaluate periodicity. A melody, for example, if it repeats itself, it's an indication of a rhythm meter. But it's only marginal. So mostly you're going to look for bursts of energy, right? So an onset detection function is a function that stays still when nothing happens on the energy front. And when there is a small burst of energy, it goes a little bit up. And if there is a big burst of energy, then it goes high up, right? So this is what this is our sort of primary signal representation that we're going to be working on. So it's important that we take good care that we have a good one. It was largely taken from a textbook from Meinhard Müller, Fundamentals of Music Processing, but adapted to tweaked to our particular need here. One thing that we first can do actually is downsampling. So this is only a step for optimization, but we can just decimate. So reduce the amount of samples by taking every other sample also. It improves efficiency. Of course, it's a very simple operation, and then you have less data to process for the entire rest of the algorithm. It introduces aliasing, yes. But here it's aliasing that doesn't hurt, and that's even beneficial, actually. Trying here to low-pass filter and remove the higher part before doing the downsampling would actually cause harm, because if you have a drum, for example, when it hits the snare, there's going to be a lot of energy in this upper band, and we don't want to filter it out, actually. It's better to let aliasing do its work and let it reflect the energy back in the lower band of the signal. And that works still quite well. So from the ORC tuning, this rock thing, was helping me here to basically determine that the target sample rate that we're looking for here is around 24 kilohertz. So we decimate by 2, basically. Most of the case, if it's 48 kilohertz, decimate by 2, 44.1, decimate by 2. If it's 16 kilohertz, leave it. Yeah, that works very well. Next thing, we take a circular STFT, so the spectrogram, and circular. Why? Because typically when you do an STFT, at the beginning of the signal, you zero pad. At the end of the signal, you zero pad, right, with your window there. But this breaks the periodicity. A loop actually doesn't have a beginning and an end. The beginning is the end. So when we do our STFT, we have to make sure that the window that goes and meets the end is wrapped back then at the beginning. Oops, sorry, wrong. Oh, no. Circular. Okay. So that's the representation that we get. Some ODF implementations do look into the phase evolution as well. For the purpose of this algorithm, it was found that just using the magnitude was sufficient, and it also has, of course, a benefit in performance. It reduces by half, again, the number of samples that you're dealing with. Next thing that we do is we do a logarithmic compression. So the spectrum that I was shown was actually already compressed. Pardon this. But the input to this guy is just the power spectrum without taking the log. And here what we do is we do something more aggressive than just taking the log. You all know that small amplitude sounds are very easily detected by the ear, right? Or changes in small energy levels are much more perceivable than changes in high, you get me? So here what we do is we really compress quite aggressively the lower energy values of our power spectrum here. You see that they quite very fast go up to high values, and then it flattens out. Now that we've done this compression, we of course go bin-wise, so time-wise, between consecutive bins, we take the difference, the positive difference. So if it's negative, we ignore it. And then we sum vertically everything. And this leads then to what already begins to resemble our final onset detection function. Let's listen to the, have we listened to this guy already? No. Yeah, so this is the sound that's behind. So the bigger peaks are the snare drum. Yeah. We have this 8-note rhythm. And these are represented by these peaks here. But it's, so all these that I've already shown really stand out from the noise floor. However, there are also those musical notes, this musical rhythm, which is on the 16th note level, and it's those little peaks here that you see, and they get dangerously close to the noise floor. So we have to do something about it. And what we do in our implementation, we just take a moving average of the entire thing. We then subtract it, and boom, it collapses the ODF to something that looks very nice for us. Let us listen to one more time to this guy. And if I go slow, then it goes do 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 do. You see here, there's nothing. Do 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 do. Ah, something is missing here. It's not perfect, but it's not so bad either. So that's what we are going to be looking at when we then try to see if we have tempo or not. And this is where the novel part or the innovation kicks in. This name, hopefully by the end of this talk, is going to be more legitimated. And if it's not, if you at the end of this talk you still find that this is a bad name and you have a better proposal, then I would be more than happy. But bear with me for now. So first, what the heck is a tatum? It's a term that was introduced by Jeff Blimes in his PhD thesis in 1993, saying it's the smallest time interval between successive notes in a rhythmic phrase. So, by example, boom, pa, boom, pa. That's my tatum rate, so to say. If I go now, boom, boom, pa, boom, boom, pa. That's my tatum rate, right? So it's like the smallest time division that you have is your tatum rate. And yeah, let's listen to this tatum rate here. A sonic visualizer renders this guy as this. Okay. Now, the idea of this algorithm is that we are going to try different tatum rate hypotheses and see how well they explain the onset detection function that we have. We have to be careful. The more hypotheses we test, the more likely it is that we get unlucky and that we actually find rhythm when there is actually no rhythm. So we have to be conservative about this. And since we are looking for music content, which probably is going to be Western music, we can actually already keep our set of hypotheses to something quite small. And here is the result of the decisions that I took by myself, but I think they are quite sensible. We are going to try 1 tatum per bar, 2 tatums per bar for 8, 12, 16, or 24. So 1 tatum per bar is quite easy to picture. It's just like if you have a pad synthesizer, maybe that's going to play, boom, just 1 chord per bar, a Pink Floyd-like. That's probably going to sound like this. Most common, from my experience, is actually the 16th, so a 16th note kind of rhythm. Here an example. That's a 16th, and that's very, very common. You see that there are some tatum count or tatum per bar hypotheses that have a factor of 3 inside them, and this is when we introduce some swing. So we saw that we only concentrate on 4/4 rhythms. We exclude ternary rhythms, but when you swing your rhythm, actually you introduce something ternary into it, and it reflects then in the tatum rate. So 12 is only for an 8-note rhythm that was swung. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 12, yeah? And 24 is when we go from 16 to a swung 16th note rhythm. Yeah, so you get it, I suppose, I hope. Yeah? Okay, good. Thank you. That's the first restriction. So we have a limited set of tatum per bar hypotheses. Now we're going to restrict to our bar count hypothesis. We know from stats that in Western music, at least, BPMs less than 60 per minute are almost as good as inexistent. And over 200, it's the same, 50 more, 50 to 200. We also know that what it is we are testing is the assumption that what was being imported by the user is a loop. And if it's a loop, there is an exact number of bars, right? So a loop has 1 bar, 2 bars, 3 bars, but it's not going to have 3.5 bars. So we can then evaluate the realistic bar counts that would imply realistic tempi. We are not going to try if the loop is 5 seconds to see if it's 10 bars in there. That would be way too fast. And this then leads to us to this set of hypotheses that we have, right? So on the x-axis here, we have the tatum per bar hypothesis. So 1, 2, 4, 8, 12, 16, 24. And our example is 5 seconds. So in 5 seconds, we can realistically fit 2, 3, or 4 bars. 1 bar would mean 48 BPM, too slow. We stop here, and 5 bars, 240 BPM, too fast. So our realistic bar count numbers are 3, 4, and 5. And the combination then leads to the overall tatum count within the example. So 8 tatum per bars, 2 bars, 16 tatums, right? And I used colors because there are some tatum counts which are explained by different bar count tatum per bar combinations. The 16 tatum count could also be 4 bars of 4 tatums, right? This is going to be of relevance when we come to the disambiguation step at the end. There is one more thing we can do to reduce even more the number of hypotheses that we try, which means less risk of false positives, is to consider then the resulting tatum rate itself. If we have a tatum count of 48 over 5 seconds, so this example here, these guys, that would mean that per second we have almost 10 tatums, and that's about the fastest I think that a normal person can perform on an instrument. So, I mean, we can try, break the ice. I am also quite nervous, I don't know. So, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, enough. So I don't play that fast on the guitar. For Yngwie Malmsteen, that's easy peasy, of course. He could probably go 96, but normally not, right? We can safely ignore these, and everything that is higher than, that implies a tatum rate higher than 10 per second can then be eliminated. All right. And now that we have our hypothesis, how do we see which one matches best, basically, the ODF that we have? And this is what we are going to look at now. We basically draw the tatum grid. And for each peak of the ODF, we take the normalized distance to the closest tatum. So here, it's actually a distance of 1, because it's right between 2 tatums. And it is weighted as well by the height of the peak. So a small peak that has a large deviation from the closest tatum is not going to be a big penalty, but the large peak is going to be. And I think that perceptually, both perceptually and from a performance perspective, makes a lot of sense. I suppose that if you're a drummer, you are going to take care that your bass kick and your snare drum nicely falls on the beat, but all the little decorations that you do around are going to be less precise, and they are probably also going to have less weight then. And then we have a little bit of tolerance here. However, the higher the tatum rate we test, the more we expect from the performance that he is precise, because otherwise, if it's a little bit janky, then it's not going to classify as a loop. But that's another limitation of the algorithm. All right. So here we see that it then perfectly falls onto a tatum, so that's 0 penalty for this guy. And I'm looking back at my at the audio example that we like to listen to. We actually know we are humans, we are musicians, we know it's 16th note rhythm, so it's actually 16 tatums per bar, but the algorithm doesn't know that yet. So let's see what it would see if we try 12 tatums per bar. Here we see that there are some coincidences, of course, but there are also regularly one that completely falls off. And the average error here is 0.3. So the error here is going to go from 0 to 1. And that's not a great fit. Say we try 18 tatums per bar, it's even worse, because the highest peaks are those which miss their target. And the error is here 0.64. And if we then give the correct tatum rate, actually also here matches then very nicely, and the error is then close to 0. Great. Okay, but there's a problem. Single events. If we get a non-set detection that looks like this, then the algorithm says, okay, I place my line so that the least square error is reduced. It yields this. We have a perfect match here, super. And here, there's no match at all, right? But there is no peak either. So the weight is close to 0, if not equal 0. And so we have a perfect fit. But single events is not something that we want to classify as loops, right? I mean, it could be maybe the hit of a snare drum, in which case you could argue, that can be looped. Yeah, okay, maybe. But I mean, if it's a clap of the hands or a gunshot, it's probably not something that we want to detect as music. So we need a defense against this. And what I imagined, and which works quite well, is to use kurtosis. So it's normally a feature of probability density functions, but we can do as though our ODF were a probability density function and see how it then correlates. To give you maybe an intuition of what the kurtosis denotes, I have taken here 3 very famous probability density functions, the Laplace, the normal, and the uniform one. I've parameterized them so that they have the same variance. And so they have the same variance, so they deviate as much from the center, one as the other, yet they have a different shape. And you see that the more peaky, the more, and the higher the kurtosis then. Okay, so that looked interesting, and if we run this on actual samples, there's actually indeed a strong correlation. Wood snare here, kurtosis of 3,000, so that's enormous. This guy, 23. Is this a single event? I don't know, it's an arpeggiation. Is an arpeggiation just a single event or not? I think we're here in the gray zone. And I think that nicely, the kurtosis is also then in the gray zone. So it's like, it's not small, but if we look at the drum loop, then the kurtosis is very low. And okay, that correlates nicely. And I ended up then choosing a threshold of 20. If the kurtosis is higher than 20, then it's a single event. We don't look further, we stop the estimation, and we say it's not a loop. All right, and now that works. That works quite well. Yeah, Tatum to beat rate. Now we have basically a Tatum rate winner. If it's a bad match, then it's not a loop. We've already escaped the algorithm. But if it's a match, we still have an ambiguity. In the end, we also have to detect take a guess as to what the BPM is, right? And say the algorithm said there is 16 tatums in this audio file, then we still have an ambiguity here to solve. It could be 8 tatums in 2 bars, like we already said, or 4 tatums in 4 bars. And the number of bars, of course, is going to influence the tempo in the end. So at the moment in the repo, we only just take the number of bars that implies a tempo closest to 120. We saw that, that was the expected value of tempo for Western music. You may think, okay, that's like, I could have done that. Yeah, I know. But there's 2 things. First thing, the Tatum quantization fit already has eliminated one of the candidates, right? We're not going to evaluate the implied BPM of 3 bars because we know the rhythm doesn't fit to this, right? So we've already reduced the final candidates. There's one thing. And second thing, it's actually not in the algorithm yet, but while I prepared this presentation, I realized, actually, I have seen it at least, that 16 tatums per bar is very frequent. When I looked for an example of only 1 tatum per bar, I had trouble. I had to really look a long time. I mean, sometimes you are going to have atmospheric pads, for example, which are going to just place 1 chord. But I suppose the performer is just not going to be able to restrain himself and boom, going to play some notes in between, right? So you're never going to have sometimes you are going to have it, but every now and again you are going to have 1 note, 1 decoration. So it's rare that you get very low tatum rates. And actually, I could integrate this in this final decision. Here it could say, 8 tatums rate, 8 tatums per bar, that's actually more likely than 4 per bar. So of course, then we also have to weigh in the resulting BPM. We don't want something to be too slow or too fast, but this could improve then the correctness of the final decision. Okay. A little bit of time on performance. That was also one of the claims in my abstract, that it was really performant. And if there is a target in the repo, that's just a command line application, that is going to download as well all the files from the data set, if they are not already on your computer, and run the algorithm on all of them. So it's a total of 140 files, which amount to 2,700 seconds. And on this guy here, here are the specs, if that makes any sense to you. It's all classified in 700 milliseconds, so we are almost at 4,000 times real time. So I think that if you use this in your product, it's not going to cause any noticeable delay of any sort. On top of this, in Audacity, and this is also something users of this library could do, is we look at the duration. If it's greater than 1 minute, then we see, I don't know, loops that are larger than 1 minute are rare. So, and they would then require more power, more time to be analyzed. So we also exclude them on top of this. So that's it. Special thanks to the Muse group, who are paying me for doing so far the best job of my life. So that's great. And to my team, who has shown a lot of support as well. They've been more than just watching me. They've also taken action to help me get this realized. And special thanks to some other projects. freesound.org, I must say, 100% respect, guys. You rock. And the guys behind VAMP and the Sonic Visualizer as well. They are the real deal. Thank you very much.